All right. Okay, so let's do the same thing for B. So we constructed something that has actually includes the boundaries, and we're going to loop over the elements, and bi is going to be equal to, now according to our other derivation, so it's the area of the triangle, right? So it's xi plus 1 minus xi minus 1 divided by 2. So my b is like that. Again, I'm choosing from 2 to n minus 1. So my b is just the middle 4 numbers. Okay, so we have actually constructed my a and b, right, according to our derivation. So what's left is to u equal to a backslash b. Here comes my solution to the problem. Okay, I get, let me see, I think I must have a problem because that's not the kind of solution I'm expecting. Oh, I'm missing the negative signs in my A. So let me go back, look at our history. Okay, and see, I have this. This is correct. Okay, my diagonal term is correct, but I am missing a negative sign. So I of I minus 1 is equal to actually minus 1 divided by xi minus xi minus 1. And the matrix is still symmetric. That is nothing wrong with that. Okay, my A is that, and A is equal to, get rid of the first row, first column, last row, last column. That's my A. And my U is equal to A backslash B. So my U is like that. All right. So my U is positive. That's something I do expect, right? Because we are solving. Remember, the equation is the second derivative of U plus F, which is 1, equal to 0. Which means the second derivative of u is negative 1, right? So it's a parabola that goes up from 0 to the top at x equal to half and back to 1, back to 0 at x equal to 1. So let's see how well that does. So let's actually, my u is actually equal to 0 in the left boundary, u, and 0 again on the right boundary, right? So that's kind of giving me the boundary conditions. And let's plot x, u to see what we get. Okay, as you can see, we have a very coarse grid. So we are kind of a missing majority of the domain here. So let's just, this is our numerical solution. As you can see, I mean, although we're just plotting the grid values, but we know the solution is a piecewise linear function between the grids, right, in the elements. So just connecting the dots actually gives us the exact form of the solution. So this is our approximation to the parabola. And let's just plot the parabola on top of this to see how the approximation looks like. So x, fine, let's say length space from 0 to 1. Let's give it 1001 points. And the u exact is going to be equal to, well, I think if I want a second derivative of 1, I need to multiply by 0.5 times x fine times 1 minus x fine. That'll give me the correct boundary condition, right? I need to dot times, and I'll plot x exact, x fine, and the u exact. Okay, so you see the red one is the exact solution, and my blue one is my numerical solution with finite elements. So you can see, although my my elements are extraordinarily coarse, I'm actually getting the solution pretty well, right? Okay, so how about let's refine the solution, refine the elements a little bit. Okay, let's let me actually make a let me add a, wait, where is it? Oh, new. Okay, let me add a script to capture the history. So let's see, FEM, and where is my A? So let me copy everything to here, and paste it here. Wait. Let's see, have a zeros. Okay, so let me just get rid of the printouts by putting suppressing the output. Okay, and I think I also need to copy my segment that computes the right-hand side. See, go back into my history, my B, yes, to here. So after I compute A, I compute B. Okay. Let me just run it to make sure I get the same plot. Let me run it. Yeah, okay. I think I need to change. Yeah, I need to get rid of this incorrect line. Let me run it again. Okay, I do get the right stuff. And let me suppress this output. So now let's choose our n elements to be a little bit more. So n elements to be, let's say 100, okay? And I'm still gonna be choosing the random numbers. Let's see, right. So that is my random number generator, and x equal to sort x, and x equal to 0, x, and 1. Okay, so that's my new elements partition. It's still random, but much funner. And let's run it to see how it gives me. All right, so that's actually now the new finite element solution. I have completely scattered out elements, right, because of the random numbers I'm generating. But you can see that the solution matches the exact solution actually extremely well. That's one of the things about finite elements, is that if you get an equation that it is suitable for solving, you actually sometimes get accuracies actually pretty much beyond what you expect. Even with another thing is that it's actually very resilient to bad meshing. If you have very non-uniform grids and very anisotropic or distorted grids in 2D and 3D, you can still get pretty good solutions with finite elements. And it can be actually pretty easily demonstrated even in one-dimensional solutions like this. All right, so that's it for today, and I'm gonna stay on Zoom for a little bit longer to answer any questions you have. All right. Okay. Thank you.
Thanks.
Thank you.
Mm-hmm.